How to debug race conditions with GDB. Have you ever faced the frustrating challenge of race conditions in your programming? If so, you're not alone. Race conditions can lead to unpredictable behavior in your applications, making debugging a critical skill. Today, we will look at how to effectively debug race conditions using the GNU Debugger, commonly known as GDB. First, let's clarify what a race condition is. A race condition happens when two or more threads access shared data at the same time, and at least one thread modifies that data. This can lead to unexpected results based on how the threads are scheduled. To get started, you need to prepare your program for debugging. Make sure to compile your code with debugging symbols enabled. This is typically done using the flag that indicates debugging, which is the letter G. Also, avoid optimizations that could obscure the flow of your code. This setup allows GDB to provide accurate information during debugging. Once your program is ready, you can utilize GDB's thread management commands. For instance, using the command to list all active threads will show you their identifiers and statuses. You can switch to a specific thread to inspect its behavior. If you want to run a command across all threads, there is a command that allows you to do just that, which is useful for checking shared states. Next, GDB has a feature called scheduler locking that can control thread execution. By enabling this feature, you can ensure that only the current thread runs while you step through your code. This prevents other threads from interfering and changing shared data unexpectedly. This isolation helps you observe how one thread behaves at a time. Setting breakpoints and watchpoints is another effective strategy. You can place breakpoints at critical sections where shared data is accessed. Watchpoints allow you to monitor specific memory locations or variables. When a watchpoint triggers, GDB will pause execution, enabling you to inspect which thread caused the change. As you step through the threads, consider using the step instruction or next instruction commands. These commands give you fine control over execution at the assembly instruction level. This lets you see how threads interact with shared variables and synchronization tools like mutexes or condition variables. If you are using POSIX threads, consider naming your threads in your code. This makes it easier to identify them in GDB, as it will display these names during debugging. Analyzing synchronization and shared memory is also important. Check how mutexes, semaphores, or other synchronization methods are used. Make sure that shared memory accesses are properly synchronized to avoid issues. You can also send signals to interrupt your program at any point. This allows you to pause execution and inspect the states of your threads and shared data conditions. Lastly, remember that race conditions can be tricky because they depend on timing. While GDB is a powerful tool, it might not reveal all issues on its own. Consider using additional tools like race detectors or sanitizers that can automatically detect data races. In summary, debugging race conditions with GDB involves controlling thread execution, inspecting threads and shared variables, and stepping through code carefully. Naming threads and understanding synchronization mechanisms can improve clarity. Combining GDB with specialized race detection tools can further assist in your debugging process. This approach will help you master software debugging and effectively fix programming bugs.